All right, so we're gonna take on a new topic today. So we'll be having our discussion will be about air pollution control and ambient air quality parameters. So for now, we'll discuss. I'm gonna discuss ambient air quality parameters with a background of meteorology. All right. So the Earth is covered by a blanket of air called the atmosphere. The atmosphere begins at the Earth's surface and extends over 600 miles into space. So it has five different layers. So before I tell you the five different layers, meteorology is actually the study of the atmosphere or the Earth's atmosphere. So that's why this air pollution, we need to study meteorology, know its basics before studying air pollution and air pollution control. So for the five different layers, we have first the troposphere. So it holds all the air plants need for photosynthesis and animals to breathe. So this is basically where we are. So we are in the troposphere. It contains about 99% of all water vapor and aerosols or minute solid or liquid particles suspended in air. So tanan water vapor in our atmosphere and aerosols, 99% of it is found in the troposphere. Also, this layer is the densest layer. So it is basically where most of the pollution and components of air are. Most of Earth's weather happens also here. All clouds that are generated by weather are found here except cumulonimbus thunderclouds. Most aviation takes place here, including the transition region. So there is a transition region between the troposphere and the next layer. So what is the next layer? We have the stratosphere. So this is where the ozone layer is found. So we know that the ozone layer protects us from the sun's harmful UV radiation. Nearly cloud and weather-free, except for some polar stratospheric clouds present in its lowest and coldest altitudes. So this is the highest part of the atmosphere that jet planes can reach. So the next layer is we have the mesosphere. So this layer has very scarce water vapor present at the top of the mesosphere, forms noctilucent clouds, so the highest clouds in the Earth's atmosphere, which can be seen by the naked eye under certain conditions and at certain times of the day. Most meteors also burn up in this atmospheric layer. Sounding rockets and rocket-powered aircraft can reach the mesosphere. We also have radio satellites found in the mesosphere. So the next is we have the thermosphere. So the thermosphere is where the ionosphere is found. So we will discuss the ionosphere later. In this layer, it is both cloud and water vapor free. Also, the aurora borealis and the aurora australis are sometimes seen here. The International Space Station orbits also in the thermosphere. In the last layer, we have the exosphere. So this is the highest layer of Earth's atmosphere, and at its top merges with the solar wind. Molecules found here are extremely low density, so this layer doesn't behave like a gas, and particles here escape into space. While there is no weather in at all in the exosphere, the aurora borealis and aurora australis are sometimes seen in its lowest part. Most Earth most Earth satellites orbit in the exosphere. So the difference between these layers, so the troposphere extends to about 10 kilometers, while the stratosphere extends to about 40 kilometers, the mesosphere 50 kilometers, the thermosphere we have 300 kilometers, and the exosphere 400 kilometers in altitude. All right. So for the thermal profile of the atmosphere, so in the troposphere here, in the troposphere, temperatures typically go down the higher you go. So this is the temperature gets colder the higher you go. Since most of the heat found in the troposphere is generated by the transfer of energy from the Earth's surface. All right. So there then we have the tropopause, or this is the transition region between troposphere and the stratosphere. So in the stratosphere, because of the UV radiation, the higher you go up into the stratosphere, the warmer temperature becomes. So the transition region between the stratosphere and the mesosphere, we have the stratopause. In the mesosphere, it gets progressively colder with altitude. In fact, the top of this layer is the coldest place found within the Earth system. So it is about maybe negative 90 degrees Celsius, right? So that's very cold. So it has an average temperature of about minus 85 degrees Celsius or negative 120 degrees Fahrenheit. So the thermosphere we have in this layer, temperatures increase with altitude due to the very low density of molecules found here. It is both cloud and water vapor free. All right, so you may ask, how does our system hold up the atmosphere? So let me show you this video.
Electromagnetism, or the electromagnetic force, is one of the four fundamental forces of nature. It generates light and energy and holds atoms, matter, and the world as we know it together. Electromagnetism is a branch of physics that studies the interactions between electric and magnetic fields. All matter has an electric charge, which can be positive, negative, or zero. Opposite charges attract, while like charges repel. These electric forces bring and hold atoms together. And when atoms gain a positive or negative charge through the transfer of electrons, a measurable electric field will form. If those electrically charged particles start to move, the field will become a flowing electric current and form a magnetic field around it. Under the right circumstances, interacting electric and magnetic fields can continuously produce and sustain one another. This generates an electromagnetic field that transmits waves of electromagnetic energy or radiation into space. The intensity of this radiation is determined by its frequency. These frequencies make up what's known as the electromagnetic spectrum. Near the middle of the spectrum is visible light, such as light emitted by stars, fireflies, and computer screens. On either side are invisible electromagnetic waves. On one end are long, low-frequency radio waves that broadcast television and radio signals, microwaves that carry telephone signals and cook food, and infrared waves emitted by fires. On the other are short, high-frequency wavelengths, ultraviolet, X, and gamma radiation. Unlike low-frequency waves, these waves can pass through the human body, making them useful for medical applications. While electromagnetism has daily applications, it's also the engine that drives the planet as a whole. Thousands of miles below the Earth's surface, a layer of liquid metals churn and flow. This generates electric currents that then produce magnetic fields that all together encompass the entire planet. Called a geodynamo, this process causes Earth's poles to attain positive and negative charges, turning the planet into a giant electromagnet. This phenomenon also creates a protective layer around the planet. It shields us from the most harmful radiation in space, leaving us to enjoy a world held together by the strange and fundamental force of electromagnetism.
All right, so that was electromagnetism. So, there is also what we call atmospheric radiation. So, atmospheric radiation, this is the flow of electromagnetic energy between the sun and the Earth's surface and is influenced by clouds, aerosols, and gases in the Earth's atmosphere. So, on the Earth's surface, the composition of air is relatively constant. Dry air, which means air that is assumed to contain no water vapor. So, we have a relatively constant composition. So we have 78.1% nitrogen, we have 20.9% oxygen, 0.9% argon, and all the others are trace gases. All right. So we have here the composition of our atmosphere also changes with altitude. So we have two separate um, two separate um, phases. So we have the homosphere and we have the heterosphere. So basically in the homosphere, so this is where our air is. So it is relatively constant in composition. So in the homosphere, the composition does not change, but as you go higher in altitude and approach the turbopause, so in the homosphere, we have turbulent mixing. So it has relatively constant composition. So we have the major components of air. We have oxygen, nitrogen, argon, and water vapor as well. So the composition is relatively constant all throughout the homosphere. As you go up in altitude, so you approach the transition region, which is the turbopause. All right, then you reach heterosphere. The heterosphere is where there is stratification, where heavy gases or gases with larger molecular weights tend to settle at the bottom and lighter gases rise to the top of an initially uniform air mixture. So, uh, so we have the larger molecular weights. We have the oxygen and nitrogen and so on. So we have the lightest gas, which is the hydrogen. So it also stratifies at the top. So grupo-grupo ang mga components sa air. So we also have the ionosphere here. So which is the ionized part of the upper atmosphere of the Earth. So this is what makes the Earth suitable to support life. So in the other planets in the solar system, so let's go first to the terrestrial planets. We have Mercury, Venus, and Earth, as well as Mars. So in Mercury, you have 22% hydrogen gas. So this is not suitable for humans to live in. Alright, so hydrogen gas, dako kayo taas. In Venus as well, we have a high carbon dioxide content. Okay, so we humans don't inhale carbon dioxide. We exhale carbon dioxide, right? Also, in Mars, the same thing, carbon dioxide. Now, in the gas giants, so these are their atmospheres mostly contain hydrogen gas and without oxygen. So that is why the Earth is very suitable, the only planet that is suitable for um, living. All right. So also, air pollution and air composition affects global temperatures. So as you can see in the diagram, so we have the diagram of this is the temperature which goes up and down. Now, as you can see here, this is the lowest dip of the temperature. So this is between 1400s to 1800s, right? So you can see here it is labeled at least 90 major eruptions. So here daghan kayo eruptions. So now why did the temperature, global temperature, dip this very low? All right. So we have mentioned before photochemical smog, or smog, basically smog. So what does the smog do? Alright? So the air surrounding the Earth is held in place by gravity. Gravity pulls the air toward the Earth's surface, giving the air its weight. Air pressure is the weight of a column of air pushing down on a portion of the Earth's surface. So before we discuss the smog, so um, there are meteorological conditions. So the prevailing environmental conditions as they influence the prediction of weather. So mo ni sila ang predict sa weather. So we have wind speed and wind direction. We have temperature, humidity, precipitation, air pressure, lapse rate, and stability. All right. So for wind direction and wind speed, so it is described uh, by a rose curve. So how do you read the rose? Let's take a look at this video.
Hey, hello everyone. This is MLive Chief Meteorologist Mark Torregrossa. Just wanted to give you a little brief 30-second rundown on how to read this wind rose. So this is for Saginaw Airport, MBS Airport, for the month of April, the average wind for the month of April. Here are the compass directions: north wind, north-northeast, east-northeast, east, and so on. And then what you see here is a frequency of how often that direction happens. So for example, see this circle out here? That's a 5% of the time. This is a 2.5% of the time having that wind. So let's take this wind direction here, almost northeast, just a little north of northeast. That occurs a little over 5% of the time in April, and then this shows you how strong the wind typically is. So about 2% or so is 8 to 13 miles an hour, and then another couple of percent is 13 to 19 miles an hour, and then 19 to 25 miles an hour, and a small percentage out of the northeast, 25 to 32. But what you do see is that there's a dominant northeast wind pattern, and then still some scattered frequencies from the southwest and the west. That's how you read the wind rose for the post in this story. Hey,
All right, so that's how you read the wind rose. All right.
hello everyone. This
Also, there is a plume pattern of stack gases that change with varying lapse rate. So, before anything else, lapse rate is a rate at which the temperature decreases as the height increases. Also, dry adiabatic lapse rate, or DALR, it is the rate at which the temperature of a parcel of dry air decreases as the parcel is lifted in the atmosphere. It is a constant if there is no heat exchange. So actually, DALR, or dry adiabatic lapse rate, is at 9.8 Celsius per kilometer. So if there is no heat exchange within our atmosphere, so the air basically, um, the temperature of the air decreases to 9.8 Celsius per kilometer, so as it goes high up the altitude. So there are different types of plumes.
Hello everyone. Today we are going to discuss about dispersion of air pollutants. Already in the previous video we have discussed about the ELR and ALR, that is environmental lapse rate and adiabatic lapse rate. Also we know that diffusion of pollutants, mainly the air pollutant, into the environment is governed by the ELR and ALR values, that means the environmental lapse rate and adiabatic lapse rate values. By comparing these two lapse rate, it is possible to predict to some extent the dispersion of gases emitted from a source. Okay, the emitted gases known as the plume and their source are known as the stack. Typical type of environmental conditions characterized by different relative positions of ELR and ALR lines are shown here. This phenomenon generally occurs in the lower atmosphere, generally less than 300 meter above ground level. So, depending on the position of ELR line and ALR line, plume patterns can be divided into 7 types. These are known as, first one, looping plume, then neutral plume, then coning plume, fanning plume, lofting plume, fumigating plume, and last one is trapping plume. So before going to discuss about the plume patterns, first of all we need to know the environmental conditions. The environmental conditions can be two types: super adiabatic condition and sub adiabatic condition, depending on the ELR and ALR positions. So if you see the graph here, for super adiabatic condition it is ELR greater than ALR. Already we have discussed these positions in the last video, though I will just introduce this one. That is, in case of super adiabatic situation, the ELR line lies below the ALR line. So why this is ELR greater than ALR? This is the lapse rate. If you see the graph very carefully, you can see in the y-axis height in meters or the altitude in meters. So at 1000-meter height, the environment temperature is 15 degrees centigrade, and at that 1000-meter height the particle is having temperature between 20 to 25. So basically the environment is having lower temperature than the particle. So the lapse rate is higher in case of environment, that's why it is having the lower temperature, and lapse rate is lower in case of particle, that's why the particle is having higher temperature. So that's why the condition is written here, ELR is greater than ALR. Similarly, the subadiabatic situation is just reverse of the previous one. That is, at a certain height, 1000 meter, the particle will have lower temperature than the environment. That means the lapse rate in case of particle is higher than the environment. That's why ELR is less than ALR, and that's why it is known as the subadiabatic condition. Okay. Now let us see the first plume, that is looping plume. in the next slide. In case of looping plume, it only occurs when the environment is super adiabatic, which creates highly unstable environment. Thus, the dispersion and mixing of pollutant, mainly the air pollutant, is rapid. In some cases, due to the presence of high turbulence, higher ground concentration may occur. Due to this problem, in the areas having super adiabatic condition, higher stacks may be needed to ensure very good dispersion of air pollutants. Okay, now come to the next slide. There is second plume known as the neutral plume. Neutral plume occurs when ELR is more or less equal to ALR. That means the value will be more or less same. Environmental lapse rate will be equal to a slightly more or less adiabatic lapse rate. In that case, plume will rise directly into the upward direction, and due to the upward movement of the smokes or gases, you can say that minimum concentration of pollutants may occur near the ground surface. Now come to the next plume. The plume name is coning plume. Coning plume occurs when two special situation is prevailing in the environment. The first situation is the wind speed is greater than 32 km per hour, and also the second situation is there may be a presence of cloud, and the cloud cover is blocking the solar radiation in daytime and terrestrial radiation in the night time. And basically the neutral plume changes to a cone shaped plume due to this prevailing condition. That means whenever the wind speed will be greater than 32 km per hour, then the neutral plume will tend to move in the horizontal direction, maintaining a cone shape. Okay, and that's why the plume name is coning plume. Also, the condition of environment lies like subadiabatic condition, where the mixing and dispersion of the pollutant is minimum. Thus, the air pollution probability increases in the surrounding area due to the presence of this coning plume. Now come to the next slide. The plume name is fanning plume. Under extreme inversion condition, due to negative lapse rate from the ground surface and up to a certain height above the stack gas exit point, the emission will spread in the horizontal direction, as it cannot go into the upward direction due to extreme stability in the environment. In that case, no vertical mixing will occur and plume will spread in horizontal direction, keeping a fan-like shape. That's why the name of the plume is fanning plume. Now come to the next slide. The plume name is lofting plume. If you see the graph carefully, then you will see a inversion layer persists from the ground surface up to a certain limit, and that limit is lower than the stack gas emission point, okay, or stack gas exit point. So basically from the ground surface to that point there is an inversion layer, and above the inversion layer there is a situation prevailing like super adiabatic condition. Due to this dual environmental situation, that is from ground surface up to a certain point inversion, and above the inversion super adiabatic condition, that's why whatever gases or smokes are coming from the stack, that cannot cross the inversion layer barrier and that cannot go into the downward direction. And due to the presence of super adiabatic condition above the inversion layer, there will be huge mixing and dispersion of air pollutant in the environment, and that's why this kind of plume, that is lofting plume, is always recommended, or you can say the most favorable or ideal situation for plume dispersion or the air pollutant dispersion, because in this case the mixing is higher above the inversion layer, and that's why minimum ground level concentration of air pollutant will occur. Okay, now come to the next slide. The plume name is fumigating plume. If you see carefully the graph, you can see this is the reverse case of the previous one. In the previous case, the inversion layer was present from the ground surface to a certain limit below the stack gas exit point. In this case, the inversion layer is above the stack gas exit point. So whatever pollutant is coming from the stack, that cannot cross the inversion layer and go into the upward direction. Also, you can see below the inversion layer there is a situation like super adiabatic situation. So whatever pollutant is coming from the stack gas, their dispersion and their mixing will be very much high, very much rapid, surrounding the ground surface. And as the inversion layer is present above the stack gas exit point, so no gas can cross the barrier and go in the upward direction. That's why from the graph also you can see that is the ground level concentration will occur very high, and that's why this is the most unfavorable situation in the environment, creating maximum pollution near ground surface. Now come to the next slide. There is the last plume known as the trapping plume. In this trapping plume condition, you can see the graph. There will be two inversion layer. One inversion layer will be from the ground surface to a certain limit. That limit will be lower than the stack gas exit point. Similarly, there will be second inversion layer. That inversion layer will be above the stack gas exit point. So basically two inversion layer is present. One is below the stack gas exit point, one is above the stack gas exit point, and between these two inversion layer super adiabatic condition is prevailing. That's why whatever amount of pollutant is coming from the stack, that will be trapped between these two inversion layer, and that's why the name of the plume is trapping plume, because the air pollutants are trapped between these two inversion layer. As the pollutant is trapped between these two inversion layer, they can only mix within this limited area, and that's why this plume is considered as bad condition for dispersion, as the dispersion cannot go above a certain height. Always it will remain in the.
Alright, so um, these plume patterns not only apply to stack gases, but it also occurs naturally. So we have actually volcanoes are stack gases. They produce plume patterns like this. This is from the Taal volcano. Alright. Initially, there is a straight or upward, what you call this, upward movement of the smog or the gases.
The Taal volcano in the Philippines has thrown molten rock into the sky, triggering official warnings that a hazardous eruption of toxic gas may be imminent. Well, let's just show you some sped-up footage of the moments earlier when the plume of white smoke that several kilometres high was then spewing up into the air. As tremors shook the area, a volcanic lightning storm developed in the column of steam and ash. Pretty sensational. Views there. A state of calamity, as it's been described, has been declared across the province of Batangas, just south of the capital, Manila. Thousands of people have been evacuated from the area. Our correspondent Howard Johnson reports from near the scene.
Taal volcano has now entered a magmatic eruption phase. Last night it was a phreatic phase where there was lots of steam and ash. Now there is lava flowing from the volcano. A weak flow at the moment, but that's causing this black smoke to billow out of the volcano, and that's affecting the air quality around here. Lots of dust and ash in the air, and that is affecting international airports in this area. New Clark City and Manila International Airport have had lots of flights cancelled and suspended. There is ash on the runway. Now if we look to my left here, you can see ash all over the floor. It's turned into a mud state in some places, and on the road on the way up here we saw people clearing that mud from the road. We also saw pineapple groves completely covered in the dust, and that's no doubt going to affect livelihoods in this area. Now the other major risk that the scientists are saying is that there could be a volcanic tsunami. If you look over here, you can see Taal volcano is surrounded by a lake. Now if there is a major eruption, that could cause the earth to move, which will displace water, and so low-lying communities on the coastline here could be affected by a tidal wave if there is a major eruption.
Howard Johnson reporting.
All right. So one of those this is one of the examples of a smog. So let's say in a normal situation, so we have pollutants escaping from different stack gases, from industries, and even from volcanoes. So in a normal situation, pollutants just go up. So the temperature, there is warm air, then it gets cooler and cooler as you go high up. When there is a photochemical smog, so there is a thermal inversion. So there is a warm inversion layer. So the smog or the pollutants stay in below the inversion layer. So in the cool air, pollutants are trapped at the Earth's surface. So why is this? Now, when there is a photochemical smog, so we know that the Earth's heat, or the Earth's heat, when the Earth's heat comes from solar radiation. It comes from the sun. Now, when there is a thick smoke or a thick smog covering a surface of the Earth, so solar radiation cannot pass through the, what you call this, cannot pass through, and so there is a inversion layer. So as you can see, the temperature is supposed to just go down, so it should only decrease. But since the solar radiation is just at a surface of the inversion layer, so all the heat goes there, and so the temperature goes up. So the air gets warm at the top of the inversion layer, and so after the inversion layer, it goes down. So let us recall that the photochemical smog is a complex mixture of O3, nitrogen oxides, and hydrocarbons. So it forms on warm sunny days when traffic is busy. So the main pollutants are the NOx and unburned hydrocarbons from motor vehicles. It is at the maximum level during morning and evening rush hours. It is also at its peak during early afternoon due to secondary pollutants. So smog can also form through smoke and fog. So smoke remains due to lack of air movement initiated by the nighttime radiative cooling of the air near the Earth's surface. So nighttime cooling decreases the moisture carrying of the air, allowing fog to form around suspended smoke particles. Alright? So the smog has synergistic effects. It has synergistic effects. So the SO2, or the sulfur dioxide, slows down the rate at which the hairs of our lungs beat. So this beating action removes the contaminant from the upper lungs. So when impaired, so kung maka-inhale ta og particulates, or these irritants have greater access to the respiratory tract. So the soot particles within the smoke offer surfaces upon which the sulfur dioxide may be oxidized to a sulfuric acid. So this is the danger of air pollution. So if we inhale sulfur dioxide, there is a chance that sulfuric acid will form inside our lungs. So this is a powerful irritant. Smog causes the bronchial passages within the lungs to become inflamed and to make large amount of mucus. So this is the danger of air pollution. So also we have air pressure. So air pressure affects dispersion of pollutants and formation of clouds. So areas of high and low pressure are caused by ascending and descending air. As air warms, it ascends, leading to a low pressure at the surface. As the air cools, this descends to a high pressure at the surface. Alright, so why is there an ascending and descending air? So let's watch this video.
Picture a circle. Here's its center, here's point A, and here's point B. Point A is twice the distance from the center of the circle than point B. Oh yeah, and it spins from its center. In 2 seconds, both points do one full revolution. But to go all the way around, point A has to go this far, while point B only has to go this far. And we all know if something travels a greater distance in a shorter amount of time, it must be going faster. So point A must be moving faster than point B. Okay, now swap out this flat circle for the Earth, and the same thing is true. All points closer to the center, say like someone in Greenland, will be spinning slower when compared to points spinning further away from it, say like people in Brazil, closer to the equator. So if we look at it all flattened out, we can picture something like this. Arrows at the equator travel faster than arrows at the 45-degree line, like we just observed. Now imagine you're a cloud that formed here on the equator. You'll have the same velocity as the Earth, but then a gust of wind sweeps you to the north, where the Earth isn't spinning as fast. Due to inertia, your speed remains the same. You don't get any faster, but everything around you is literally traveling slower, so you, relative to the ground, move ahead of everything else. If you're a cloud that forms at the 45-degree line, you'll also have the same speed as everything around you, but if you drift down to the equator, you'll be moving slower than the ground underneath you, so you'll fall behind. And the same things for the southern hemisphere. Moving towards the equator always results in falling behind, while moving away results in pushing ahead. Okay, now imagine a low-pressure cell. That means all the air around it will get sucked into the center. But the air coming from the equator will be traveling faster, so it will deflect to the right, while the air coming from the poles will be moving slower, so they'll fall behind and deflect to the left. What this results in is a circular air current spinning counterclockwise, and that's exactly what hurricanes are, low-pressure cells spinning because of the Coriolis effect. Moving this example down to the southern hemisphere, things are reversed. A low-pressure cell will still suck in the surrounding air, but now the air coming from above will be moving faster, again deflecting to the right, while the air coming from below is moving slower, again falling behind by moving to the left. This results in a clockwise spin, which is why storms in the southern hemisphere spin this way. And that's about it. It's a short video.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
That's why it spins in that direction and in that way, because of the Coriolis effect. Alright, so in a Coriolis effect, if there is no rotation, so it's basically a simple circulation pattern. But with Coriolis effect, that is due to the rotation of the Earth, creates large-scale eddies with belts of wind and belts of calm. So these are eddies right here. So those due to the rotation of the Earth, the Coriolis effect happens. All right. So this is the Coriolis effect. So now, if you look at weather updates or the news, you could see how the air moves. All right. So this is actually due to the Coriolis effect. See, this is wind direction. All right. Now, so how do we, let's now go to um, ambient air quality parameters. So how do you monitor areas, air pollution in areas? So like water pollution, they have a watershed. So a watershed is basically the area at which the water quality is deemed the same. So it's the same as a watershed. So an airshed is areas with similar climate meteorology, and topology, which affect the interchange and diffusion of pollutants in the atmosphere. So it is similar with a watershed, but it has a large scope and area. So there are no sharp boundaries, unlike the watershed. So this is the watershed of Cagayan de Oro. So there is a map of the Cagayan de Oro River. So, but according to DANR, so the airshed, we belong in the same airshed, Cagayan de Oro, municipalities of Hasaan, Villanueva, Taguluan, Opol, and El Salvador. So this is one complete airshed. So this is here from El Salvador, Opol. We have El Salvador, Opol, Cagayan de Oro, Taguluan, Villanueva, and Hasaan. So this is one complete airshed. Now, there are two ways at which pollutants are deposited back to the Earth's surface. So we have dry deposition and we have wet deposition. So in dry deposition is basically the process where pollutants from the atmosphere go down and are deposited on the ground. So that is what you call deposition. Now in dry deposition, so there is a free fall to Earth directly from the atmosphere of atmospheric trace gases and particulate matter. So in dry deposition, particles and gases may deposit to surfaces quickly or may react during atmospheric transport to form larger particles that can be harmful to humans. So there is a turbulent diffusion. So gases and small particles may react because there is a turbulent diffusion to form larger particles, and so the larger particles go down. Since it is heavier now, it goes down and sediments on the surface. Now in wet deposition, the process whereby atmospheric gases mix with suspended water or water vapor in the atmosphere and are then washed out through rain, snow, or fog. So there is in-cloud scavenging and below-cloud scavenging. So in-cloud scavenging, scavenging means collect. So where there are clouds, it collects gases and small particles in the clouds. And when it rains, the pollutants or the pollutants within the air mix or are being collected through the rain. Alright, so that is actually what acid rain looks like. So
acid rain. Acid rain or acid deposition occurs when sulfur dioxide and nitrogen oxides react in the atmosphere with water, oxygen, and other chemicals to form various acidic compounds such as nitric acid and sulfuric acid. The acids fall to the ground from the atmosphere in wet or dry forms. This can include rain, snow, fog, hail, or even dust. Forms of acid deposition. Acids can be deposited in two ways. One is wet deposition, and another is dry deposition. When acidic materials falls from the atmosphere to the ground in wet form, such as rain, snow, sleet, hail or fog, etc., then it's called wet deposition. On the other hand, When acids deposit on the Earth's surface in a dry form such as dust or gases, then it's called dry deposition. Acid rain is measured using a scale called pH. Pure water pH 7. But normal rainwater pH 5.4 to 5.6. And acid rainwater pH 4.2 to 4.4. Normal rainwater is weakly acidic. Why? This is because it reacts with carbon dioxide in the atmosphere and forms mildly acidic carbonic acid before it becomes rain. Acid rain formation. In acid rain, sulfur dioxide undergo oxidation and then react with water, resulting in the formation of sulfuric acid. Reactions. Carbon dioxide reacts with water to form carbonic acid. Sulfur dioxide gradually oxidizes to form sulfur trioxide, and sulfur trioxide reacts with water to form sulfuric acid. Nitrogen dioxide reacts with water to form nitric acid. Effect of acid rain. Acid in the air react with calcium carbonate of marble and makes yellow in color. It damages the statues, monuments and tombstone made up of stones and metals. Acid rain decrease the pH level of water. Low pH level kill fishes, their eggs and fish food organisms. Acid rain also damages high-altitude forests. Moreover, it limiting the soil of essential nutrients available to them.
All right. So that is how acid rain forms. Now there are different pollutants that are involved in making the air unsafe and unclean. So we have natural and anthropogenic emissions from the air. So we have methane, carbon monoxide, carbon dioxide, volatile organic carbon, sulfates, black carbon dust, dinitrogen oxide, CFCs, NOx, and ozone. So here in the troposphere, we have the tropospheric ozone. So there is a chemical transformation, and so this tropospheric ozone is actually harmful to the environment. But if the CFCs go up, yes, it goes up, so it actually reacts with the stratospheric ozone, so it destroys the ozone layer. All right. So also, not only from the Earth's surface we have sources of pollutants, we also have pollutants in the atmosphere. So we have aircraft emissions. All right. So these are examples of natural calamities that also affect the air quality. So volcanic eruption. So in the Philippines, we have 352 volcanoes, and 22 of which are active and 27 of which are potentially active. So this is Mount Mayon in September 2014. That's 6 years ago. 8 years ago, sorry. So we have many volcanoes here in the Philippines. We have Mount Hibok-Hibok, Mount Pinatubo, we have Taal, we have Canlaon, and so many other active volcanoes in the Philippines.